All right, so this is what, worksheet from chapter 11. We're doing the multiple choice ones, number 3. So it tells us the wheel has a radius of 0.5 meters, rolls without sliding. It gives you the angular acceleration of 6 radians per second squared. It says the distance traveled by the center of the wheel from t equals 0 to t equals 3, and it wants to know how far it goes. And it starts from rest. Okay? So I know that my omega I is 0 and my vi is 0. All right. Did you get a different answer than what was on there, Mickey? Or
no, I did it wrong. I integrated instead of combining, so I got 0.
oh, gotcha. Okay. Do you want me to run through it?
No, I know it's all done.
Oh, okay. Does anybody want me to go through it? Oh, all right. Dynamite. Cool. Yeah, Matt, what do you got? Which one? 7? Solid sphere, and I should have pulled these up and put them on the screen. All right, so it says a solid sphere and a solid cylinder of equal mass and radius are simultaneously released from rest on the same inclined plane, sliding down the incline. Then it wants to know which one gets to the bottom first and why. All right. So first of all, you guys, I guess is this idea. So So when you're talking about a thing rolling from rest down an incline, the idea is you're going to start out with some amount of gravitational potential energy, right? Is everybody cool with that? All right. Then by the time you get to the bottom, you're going to have kinetic and rotational kinetic energy, right? Okay. So let's do this. Let's see if we can write an expression that kind of explains what's going on here. All right. So the idea is the mechanical energy at the top is going to equal the mechanical energy at the bottom, right? Okay. So mechanical energy at the top that's the gravitational potential energy. Oh, sorry, mgh. Sorry. So the kinetic energy at the bottom is 1/2 mv squared, right? And then the rotational kinetic energy is going to depend on our I, right? So I, the general way we've been writing I when we don't know what the shape is to use beta times mr squared, right? Everybody good up to there? All right, so with this in mind, do you guys remember what does the rotational kinetic energy end up being? How do we write an expression for the... What do you got? BKT, yeah. So it's beta times this kinetic energy. So it's beta times 1/2 mv squared, right? Cool? So first of all, it looks like my masses are going to cancel out. Did we already do all this calculation? I don't know if we've done this exact calculation. All right, so let's solve for v. So if I simplify this, bear with me here. When we get to the end of this, I'm going to show you something, and it'll be like a big thing that you can remember, like a useful thing. So bear with me here. All right, so let's multiply by 2. You get 2gh equals v squared plus beta v squared, which is the same as 1 plus beta times v squared, right? Cool. So it looks like v at the bottom is going to be 2gh over 1 plus beta, and then you got to take the square root, right? Follow? All right. So look, you guys, the smaller your beta is, the bigger your velocity is going to be, right? So it turns, and look, the mass doesn't matter. You see what I'm saying? The masses all cancel out. So what this tells us, you guys, is when you roll something down a ramp, the only thing that determines how quickly it goes down to the bottom, apart from the angle, is this beta. Okay? So, why do we care? Well, here's what we know. We know that a hoop has a beta of 1. We know that a hollow sphere has a beta of 2/3. We know that a solid disk has a beta of 1/2. We know that a hollow disk, wait, what am I doing? Oh, solid sphere, thank you. We know that a solid sphere has a beta of 2/5. So no matter what, any solid sphere rolling down a ramp will beat any of these other things rolling down that same ramp. The only thing that matters is that beta. Matt, does that make sense? Everybody, does that make sense? All right, so which answer does that correspond to now is what we got to figure out, right? So a solid sphere and a solid cylinder of equal mass and radius are simultaneously released from rest on the same inclined plane. Then, so first one, which one's going to get to the bottom, you guys? The solid sphere or the solid cylinder? The sphere, right? Because it's got a smaller beta. All right. So that means it's got to be either A or C, or E maybe. So A, let's see, the sphere reaches the bottom first because it has greater inertia. Not necessarily, because you could have the solid disk could be super, super huge. You could have oh wait, no, they have the same mass and same radius. Right. Okay. Yeah. Right. So that doesn't work. Okay. Okay. Right. Yeah. So it's not A. C. The sphere reaches the bottom first because it picks up more rotational energy. That's not true either, right? Because they both have the same mass. That means they're both going to start with the same GPE, right? So the sphere is going to get to the bottom with more kinetic energy. It's going to have less rotational energy, right? Make sense? So it's actually E. None of them is true. Good, you guys? That's dirty pool, and it's none of the above, right?
You have to figure all that out, and then it's...
Yeah. So, okay, but so you say you have to figure all this out. This is a thing you guys should remember. Beta is what determines how quickly something rolls down a hill. That's the moral of this story. Okay? Good? Okay, cool. What ones do you guys want to look at? 9? 2 uniform cylinders have different masses and different rotational inertias. They simultaneously start from rest at the top of an inclined plane and roll without sliding down the plane. Well, they're both uniform cylinders, so they both have a beta of 1/2, right? So they're both going to get to the bottom at the same time.
I think it's a different rotational energy.
Right, and I guess that's sort of what I'm trying to show you here, is that even though there's more inertia, it's got more inertia because it's got more mass. It's also going to have more force creating torque to make it rotate, so there's going to be more gravity on it, and everything ends up kind of balancing out. Any 2 spheres of any radius will roll down at the same rate. Any 2 disks, sorry, is what I was trying to say, of any mass and any radius will roll down at the same rate. Cool? I feel like we should try this. Do I have another cylinder besides this thing? Who's got a little chapstick too?
Oh, I can do it out.
You got one?
Yes.
Ooh, thank you. Oh, I don't know though. So what? Why might this not work? Yeah, it might not be uniform density. Okay, so that would be the only thing that throws us off. What have you got? All right, well, let's see what happens.
I don't know why I glue stick, but I do. It's disappearing purple too. It's, you know,
Ooh.
glue. I also have some crazy glue, but
Oh no.
Mr. Tucker?
Yeah?
I have a little pocket tape you want that. Hollow as well too.
Um,
tape right there.
Yeah, you know, I thought about doing this and this, but that the I equals mr squared assumes that the radius is much bigger than the thickness, and the hockey tape and this tape, that's not really true, you know what I mean? So.
I'm not different dots. Two dots in different sizes.
Nah. Alright, I'll see if I can find a smaller disc. Thank you.
Two dots in different sizes rolled up.
So theoretically, yeah. Yeah, so they have the same inertia, right? Or the same beta. Okay, questions on the front page for the multiple choicey stuff? Going once. Twos. Sold. All right. 10 through 14 multiple choicey. Yeah. 12 and 13. Let's see. Number 12. Two identical disks with rotational inertia, I, parentheses in a weird spot there, I equals 1/2 mr squared, roll without slipping on a horizontal floor and then up inclines. Gotcha. Disk A rolls up the incline without sliding. On the other hand, disk B rolls up a frictionless incline. Otherwise, the disks are identical. Disk A reaches a height of 12 centimeters above the floor before rolling down again. How high is the other one going to go? Okay. So first of all, which one's going to go higher, you guys? The one with friction, right? We talked about that in class, right? Okay, so now we just got to do the math on it, right? Okay, so let's.
I got confused why Lawrence rolled, but I get that.
Okay, are you sure? All right. Is there somebody else who would like me to do that same one? Number 12. No. Okay. Let's do 13 then. Okay, so 13, a solid wheel with a mass of M. Oh, right. Okay, so 13, let's see. So let's see, we've got a solid wheel, so that means our I is 1/2 mr squared. Mass M, radius R. It rolls without sliding on a horizontal surface. A horizontal force F is applied to the axle, and the center of mass has an acceleration A. The magnitudes of the applied force and the frictional force, respectively, are, okay, we got acceleration A. All right. So, because this thing is rolling, there's another force on it besides this applied force F. What other force has to be acting on it? Friction, right? Which way is friction going to act? To the right or to the left? If we pull it this way and it's rolling without sliding, then it's got to roll this way, which means around this pivot point there needs to be a frictional force that goes this way, right? Good? Right? So what we want to do is we need to see if we can come up with a net force equation that explains this acceleration, and a net torque equation that would give us that same acceleration, right? So to me, it looks like F minus force of friction should equal ma. Good? All right, so that's one of my equations. And then my other equation is about torque. So basically it's going to boil down to this. Torque is I alpha, and that's also going to equal some force times some radius. So I guess you could do it two ways. My guess is probably your intuition tells you to pick this as the pivot point, which then means that this is your radius, and so the force providing the torque is friction, right? Follow? Good? All right, so let's do a couple little substitutions here. Our I is 1/2 mr squared. Green. I've tried to change the thickness of the green marker like a billion times, and it just doesn't stick. All right, so 1/2 mr squared times alpha, which is really A over R, right? Right? Is A over R? Yes. Sorry. Oh yeah, this works. Sorry. Equals FF times R, right? Oh, yeah, cool. Sorry. All right, so is everybody good with this? You guys back okay?
Yeah.
All right. Okay, so if we simplify things, check it out. This R cancels. Oops, sorry, I wanted that to be a different color. This R cancels one of these R's, and that now I've got an R over here, and I've got an R over here. Oh, my force of friction is 1/2 NA. Cool? So, I don't know, what we're trying to find. We're trying to find what two things? F and FF? Are those the two things we're trying to find? Where did I put my, where did I put the thing? Right here. So one of the options, let's see, 3 of the options have this as a choice for force of friction, right? So B, D, and E all have that. So we got to come up now with an expression for F. All right, well, let's do that. Let's see. So F minus 1/2 MA equals MA. And then add MA to both sides, and you get F equals, well, this is 1 MA, plus 1/2 MA is 1.5, or 3/2. So you want the one that has those two choices, which is E. Follow, you guys? That's a good one because it's no numbers, so you don't get bogged down with the calculations, right? It doesn't take super long. And like I said, it's another one of those problems where you're setting up 2 equations, one for net force, one for net torque. Okay. Everybody good? Okie dokie. Any of the other multiple choice ones you guys want to look at? 10. 5-kilogram ball rolls without sliding from rest down an inclined plane. A 4-kilogram block mounted on roller bearings, totaling a smaller mass, rolled from rest down the same plane. At the bottom, the block has more speed, less speed, blah, 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 blah. Okay. Thoughts? Somebody want to take a stab at explaining this one?
Oh, well, I'm trying to work this, but so I was thinking that since your rotational inertia is has to factors your mass into it, if you have basically you can think of all 3 balls essentially, you can just think of it as one big ball, and excluding friction or anything like that, but
Sure.
with and since it's a much less magnitude, the inertia will be far lower, so it'll gain apart. You can rotate much faster. So at the bottom of the block, the bearings will have greater speed than the ball.
Yeah, basically. Yeah, so when you've got a ball rolling, all of its mass has rotational kinetic energy, right? And therefore, as it's going down the hill, it's got kinetic energy and rotational kinetic energy. But since all of the mass is rotating, there's sort of a large percentage of your total energy that's devoted to making stuff roll, right? Whereas when you're looking at something that's mostly big, that's the worst sentence anyone's ever said. When you're looking at something that's mostly big, stick with it, but then you've got these tiny little wheels, percentage-wise, there's not that much energy devoted to making these tiny little wheels roll. Most of your energy is just the linear kinetic energy of the object itself. Does that make some intuitive sense? All right, and it's the reason why if I do this, the cart wins by tons. Oh no, ducks! Okay, because yes, these wheels have rotational kinetic energy, but as a percentage of the total energy, it's a very small amount. Make sense? And that's why we can safely do this and have this be a simulation of a frictionless surface, right? Because there's not that much of the energy devoted to making those tiny little wheels. Make sense? Okay. All right. What else? Any of the other multiple choice ones you guys want to look at? Okay, cool. How about concept ones? 3, 11, or 12 were on there? Yeah.
Just for 3, can you just explain the area thing one more time? It's like the line.
Is that the one with the little drawing here? Gotcha, yeah. All right, so this is another one. I don't know, I've never taught this before, so I haven't sort of built up a wealth of ways to explain this. So you're unfortunately going to basically get the same explanation again.
Yeah, that's fine.
All right, so the way that I like to think of rolling, there are 2 ways you can think of rolling. So pretend this is a circle, right? So you can picture it pivoting around this point, right? So that it, does this, right? To me, the way that makes a little bit more intuitive sense is to instead think of it as tipping over, right? And so when you think about it that way, instead of choosing the center of your object that's rotating as your pivot point, you're choosing this as your pivot point. Good? Now, when you have a string wrapped around the axle, the force is going to be applied at that axle, right? And so basically what it boils down to is you need to figure out, with this being your pivot point, what direction is the torque from the spring going to make the wheel sort of tip over, right? And so the idea is, I mean, obviously if I pull this way, well, I shouldn't say obviously, because it's not at all obvious, but this drawing, I think, makes it clear that here's my radius, here's my force, so it's going to rotate forward, right? Does that make sense?
Yeah.
All right. If you pull straight up, this is tough to see. Maybe I should have made my radius bigger. Let me do this. I'm going to exaggerate the radius of that center spool. Oh, damn it. Okay, so we already did this, right? So that makes it this way. What if instead I pull straight up? Where's the lever arm here? Where's my R? It's this little horizontal bit, right? Do you guys see that? Right? Because it's pivoting around this point. So if I pull up on it, I'm going to make it tip back this way, aren't I? You guys see that? It's the same as if I pull up over here, right? Making it tip that way. Okay? So that's going to make it rotate this way. All right? So what ends up being the dividing line is this sort of imaginary line. Okay? So, you know, if your force producing the rotation is below the dotted line, it's going to cause torque this way. If the force producing the torque is above the dotted line, it's going to produce torque the other way. And if you pull this way, it doesn't produce torque around this point. So then one argument would be to say, well, but it's still going to cause rotation around this pivot point, and it'll spin that way if it's frictionless, but not actually tip over. And then the other argument is that, well, it'll just slide horizontally. And I haven't sort of come up with a great, sometime I need to sit down and monkey with it a little more, and I just haven't had a chance to do that. And I've, like I say, seen different sources. And David is referred. Is it David? Ethan, right. Said that the book says it spins in place. The videos I've watched say it's locked. Okay, good? All right. Did that answer the whole question? Does that hit everything? All right. Where did I put my sheet? That's the answers. Oh, here. Okay. All right. Any other concept you guys want to look at? Okay. How about problems? How'd these go, you guys? Was this apparently not terrible? Yeah.
I was having trouble with the concept of acceleration with something rolling, so if we remember more.
Yes. You see that? Weird. Okay, sorry. What am I doing? Number 4? All right. A uniform solid sphere rolls down an incline. A says, what's the incline angle if the acceleration has a magnitude of 0.10 g? Okay, so here's the short answer. I don't know that this is the answer you want. Let me give the short answer, and then if you guys want a longer answer, I'm happy to give one, okay? But in the notes, what we learned was that if an object is rolling, then the acceleration is g sine theta over 1 plus beta. So basically, all you're going to do is you're going to say, well, I want my acceleration to be 0.1 g, and that's going to equal g sine theta over 1 plus beta. The g's cancel out, and then you solve for theta.
You show why again.
So, right, so then, yeah, exactly. So then, well, where does this equation come from, right? I just showed this to Mr. Hernandez last hour. So let's see. So the way that you do it, it boils down to basically some algebra. So what we're going to do is we're going to say, all right, well, let's assume that this is an angle of theta, right? And our ball is it a ball? What is it? It doesn't even tell us this shit. So whatever, we'll just uniform solid sphere. Let's stick with the generic beta, okay? So the idea is it's going to roll some distance down the thing, right? From a height of d sine theta. So that's where your sine theta comes from. Good? And so the idea is at the top of the ramp, all of my energy is gravitational potential energy. So at the top, I'm going to have m times e, sorry, I'm doing it again. I'm going to have m times g times this height, d sine theta, right? Cool. Now that's going to equal, well, as the ball rolls down, you're going to lose the gravitational potential energy and convert it to kinetic, right? So at the bottom, you're going to have kinetic energy and rotational kinetic energy. Cool. So your masses cancel out. So let me pause for a minute. I hope I'm not making light of this. This is a super, super powerful method for solving problems, is to say, here's an expression for the total energy at one point, here's an expression for the total energy at another point, set the two equal to each other and solve for some missing thing. Okay, that's a very, very common technique for solving problems. All right, I'm working right now through chapter 13, which is gravitation, and this is all over the place. So, all right, so if I solve this mess, I get, or if I simplify this mess, I get g d sine theta equals 1/2 times 1 plus beta v squared, right? Solid? All right, so the last substitution then is this. 2a delta x, I guess quantity is v, I guess. 2a d equals vf squared minus vi squared. But in this problem, what's our vi? Vi 0, right? At the top. So this goes, oh, this goes away. That wasn't what I wanted to happen.
That's a good one.
So this goes away, and so this v squared is really just 2ad. So I'm going to take this v squared and replace it with 2ad. So now I get g d sine theta equals 1/2 1 plus beta 2ad. And look what happens. Let's see, the d's cancel out. 2 times 1/2 is 1. So now to solve for a, just divide by 1 plus beta. So that's not super sort of enlightening, you know what I mean? Like, it doesn't tell us a ton about sort of why. The way that I like to think about it is this, that if it was just sliding, then you guys know that you get diluted gravity, right? So that's g sine theta over 1, right? And then tacking on the plus beta is like saying, oh, but we got to account for the fact that some of this is going to be rotational acceleration. And so that decreases your sort of overall acceleration. Does that make a little bit of sense? All right, good. Cool. So A, we talked about how to find the angle. And then do you guys understand that a frictionless block will go faster? Right, because there's no beta, right? Your beta is 0. And because all of your energy becomes translational kinetic. Okay, what else, you guys? 7? Is that the one about the disc rolling off the roof? Cool. Anybody else? For whatever reason, I have a really tough time when they make their objects moving left instead of right. Bother anybody? Just me. Does it? Okay. Because I want to, like, I kind of want to flip the whole drawing around and make the roof go this way, but I don't want to mess anybody up if you already made a drawing. So I will not do that. All right. So here we go. So we got a roof that is a length of L, The ball's going to start up here, it's going to roll down the roof, and then it's going to go off the board because I did not keep my board space very well. Oh. So the ball is going to go down the ramp and then down onto the ground, right? All right, so here are the things we know. We know that this angle, oops. We know that this angle in here is theta. We know this is a height of h. We know that the cylinder, this is number 7, by the way. We know that the cylinder has a radius of 0.10 meters. We know it's got a mass of 12 kilograms. It's going to roll a distance of 6 meters down a roof that's inclined at an angle of 30 degrees. A, what's the speed as it leaves the roof? B, the roof's edge is at a height of 5 meters. How far horizontally does it go? Yeah. I'm not excited about part B. I think we got to use projectiles. No projectiles. I agree. Shoot, I'm wishing that that problem allowed us to just use conservation of energy to find the thing at the bottom. That would have been a better question. Okay, anyway, incidentally, real quick, this is not what the question asks us. Well, let me do part A, and then let's talk about part B. Okay, so part A, we got to find the velocity down here. So, I mean, this is almost the exact same thing as what we just did. So I know that this L here is 6 meters, right? So this is already called H, so let's call this, how about HR, as in height of roof. So since this is 30 degrees, this is just going to be 3 meters, right? Everybody good? All right, so this is literally what we just did. So up at the top, all of our energy is gravitational potential energy, right? So up at the top, our energy is mgh. Okay, and then when the ball gets to here, I'm sorry, HR. I mean, I guess it doesn't matter. Oh, we don't know this H, do we? Okay, so yeah. Isn't what? You sure? Okay. All right. Does it? Okay. So let me do my setup and then let me make a quick comment. All right. So what I'm doing to solve this problem is I have decided to call this a height of 0, and I'm measuring everything up from there. Okay. And for the context of this problem, that works just fine because our ball never goes below that point. And even if it did, honestly, you can just then make your height negative. It still works. It's weird, but it works. Okay, so anyway, so at the top we've got gravitational potential energy. When we get to the bottom of the roof, all of our energy is kT and kr, right? So 1/2 mv squared for translational plus, what kind of ball is it? Solid cylinder. So I for a solid cylinder is 2/5, right? Everybody good? What happens? Oh, it's a solid cylinder? You guys said that, and I heard you wrong. I heard what I wanted to hear. Thank you. Solid cylinder would be 1/2. Thank you. Sorry? Okay, so the masses cancel. You actually don't even need this mass to solve the problem, which is worth noting. So mass cancels, mass cancels, mass cancels. And you get G times the height of the roof plus 1/2 and 1/4 is 3/4. Oops. Sorry. Equals 3/4 v squared. And solve it. Okay, so that was the next thing I wanted to say. Now, if you want to make the ground a height of 0, it shouldn't matter, because what ends up happening is it subtracts out. So watch what happens. So this is option one, and I think the better option. But if you really wanted to, there's no reason why you couldn't call this a height of 0. Okay, and watch what happens. I'm going to set up my equation again. So up at the top, my gravitational potential energy is going to be m times g times h, whatever h is, plus the height of the roof, right? Follow? So this plus 3. Okay? Then when you get to this point, now you're going to have kinetic energy, you're going to have rotational kinetic energy, and you're going to have potential energy. But notice, if you distribute this, you get mgh plus mghr, and then mgh plus mghr, and then you just subtract mgh from both sides, and then you end up with what we had to begin with. So it really shouldn't matter. All right, what's usually, this is why it doesn't matter where you set your height equals 0. I don't know if you guys remember me having that conversation with Carson a few weeks ago. It doesn't matter because what usually matters is the change in potential energy, which is determined by the change in height. And no matter where you set a height of 0, if I walk from here to here, it's always the same vertical distance, no matter what I call a height of 0. Does that make sense? Everybody? Okay. All right, so do you guys see how to solve that then from there? Notice this is another one of those things. Total energy at one point equals total energy at another point. All right, now, here's the question. I'm about to do this, so I apologize. This is probably annoying. Here's what I wish question B had asked, and I'm going to change it for next year. I wish question B said, what's the velocity when it hits the ground? What's the velocity of the ball when it hits the ground? So here's all we would do. So when the ball goes off the edge here, it's going to have gravitational potential energy, right? And kinetic energy, right? It's also going to have rotational kinetic energy, but that's going to stay the same as it goes through the air, isn't it? Do you guys see why? All right. So when it hits the ground, it's still going to have that rotational kinetic energy, and the translational kinetic energy will just equal whatever the GPE was plus whatever the KE was. Does that make sense? In other words, conservation of energy is a super badass way to solve projectiles problems. Because you don't have to worry about any angles. Do you see what I'm saying or no? So that's a really cool trick. And when I assigned this problem, I apparently didn't read it as carefully as I should have. I thought that was what they were going to have you do. All right. Unfortunately, they didn't, and I think that there isn't a cool way to solve part B without using a bunch of kinematics equations, and we can certainly do it. I don't know that it's super instructive at this point. Before the AP test, I hope to spend a little more time with projectiles, because that was a section that I think we struggled with, we as a unit. So I want to make sure we spend some more time on it, but I don't know that right now is the best time to do that. Is that cool?
What's the answer?
Oh, is it not on there? Oh, I don't know. Where's my book? The answer to number 7 is 4 meters. And the answer to A, wait a minute. Oh, we're trying to find the angular speed as it goes off the roof for A. Wow, I got an F minus. Yeah, but yeah, so you can just do B over R, right, to find your angular. Yeah, you guys are exactly right.
What's the answer?
63 radians per second. Sorry to put the answers on there, I guess. All right, are we good? Okay, cool. Yeah, and I'm looking now at my solution for B, and it's just a bunch of kinematic stuff. You have to find this velocity, the velocity as it goes off the edge, and split it up into components. And then use your initial vertical velocity and the height to find the time, and the horizontal velocity and the time to find the displacement. It works, it's just easiest. Okay, what else do you guys want to look at? How about these ones with the graphs? Were we okay with like 6 and 8?
You do six.
6? Sure. Okay. Yeah, so to solve 6, we're going to go back to, where is it? This equation, I think. All right, so put that in the back of your head for a second. All right, so here we go. Let's see. We've got this graph. It says the graph at the right gives speed versus time for an object with a radius of blah, blah, blah that rolls down a 30-degree incline. The scale on the velocity axis is set by that. What's the rotational inertia of the object? Okay, so oh, right. Gotcha. Okay, so here's what you're going to do. Based on the graph, here's what I know from number 6. I know that my velocity at time 0 is 0, and I know that my velocity after 1 second is, if you read the graph, and I made this mistake, it's not 4. The velocity after 1 second is 3.5 meters per second. So take a look at the graph and make sure you understand where I'm getting that. Does everybody see that? There's like 8 boxes going up, right? 4, so each box is half a meter per second. Good? All right, now, that graph is a straight line. It's a velocity time graph. So that fact that it's a straight line tells me constant acceleration. So find your acceleration. It's just v minus v naught over t, right? So 3.5 minus 0 over 1, you get 3.5 meters a second squared, right? Make sense? Okay, well, and it's about a thing rolling smoothly down a ramp. So that should be equal to g sine theta over 1 plus beta. And I know the problem told me that theta was 30 degrees, and obviously I know what g is, so I can algebraify this mess and figure out what beta is. And if you do that, beta turns out to be 0.4, or 2/5 if you prefer fractions. So it's a solid sphere. Whoever just said that, yes, good job. Or maybe, could be something else with that same beta by chance. But brain, go. Oh, great. So now we got to find I, right? Well, so I is beta times mr squared. We just found beta, and the problem gives you m and r. Keep plugging your numbers. Well, this is, what I need to do is I need to keep a list of like equations that you guys need to memorize that aren't on that equation sheet. This might be one of those ones that like, it feels like it comes up fairly often and it's a fairly useful equation. It's not terrible to derive, but you know. Good? All right. All right, we got a couple more minutes. We can go through a short one. Did we do okay with 8 or no? I don't remember what it was about now. Oh, it's about turning points, right? So remember, that's the point where your total mechanical energy is the same as your potential energy, because that means your kinetic energy is 0. Are there any short ones that are jumping out at anybody? We can spend more time on this next week if we need. Okay, cool. I've been talking for now. I'll shut up. All right, cool. So I put sort of a tentative schedule on the board for next week.